Section 2.3, Continuity. Any function y equals f of x whose graph can be sketched in one continuous motion without lifting the pencil is an example of a continuous function. Example 1. Find the points at which f is continuous and the points of which f is discontinuous based off this graph. So looking at this graph, we can determine continuity if we can sketch out the graph without having to lift our pencil. So I'm going to try to do that now. So I'm going to trace this, and I notice that right here I have to lift my pencil in order to continue the graph. So then at x equals 1, we're going to have a point of discontinuity. So then I continue my graph, and then here, since I have a hole, I have to lift my pencil, go to this blue dot, and then lift my pencil again. This means I have another point of discontinuity, and now I can complete the graph without having to lift my pencil. So at this point here and this point right here, I'm going to have discontinuities. So the way we answer that is by writing f is continuous at all points on the interval 0 to 4 except at x equals 1 and x equals 2. It's important to point out that I included brackets. That means my endpoints are included. If I were to use parentheses, the endpoints of this function would not be included. Now I want to talk about the definition of continuity at a point. There's a couple things that go into this definition, so you might have to take some time to copy it all down before we go over it. A function y equals f of x is continuous at an interior point. So continuous at an interior point C of its domain if the limit as x approaches c from the left of f of x is equal to the limit as x approaches c from the right of f of x, which is also equal to f of c. Let's take a minute to remember what this part of it means. If the limit from the left is equal from the limit from the right, that just means that the limit exists at the point. So all we need to determine is that if the limit output is equal to the function's output. So for example, if the limit as x approaches 5 is equal to, say, 2, then f of 5 also has to equal 2. Up to now, it has not mattered whether the function evaluated at the point is an actual y value. All we've cared about is the limit from the left and limit from the right. However, with continuity, the limit from the left and the limit from the right also have to equal the function evaluated at that point. Now we're going to talk about what it means for a function to be continuous at a left endpoint or a right endpoint. So a function y equals f of x is continuous at a left endpoint, a, which is just an x value, or is continuous at a right endpoint, b, of its domain if the limit as x approaches a from the right of f of x is equal to f of a. And again, that's our left endpoint, so this is continuous for a left endpoint. So if we have a graph like this, it's continuous if the limit is equal to the evaluated point, or for a right endpoint, the limit as x approaches b from the left of f of x is equal to f of b. This means if you have a right endpoint, then the limit as you get close to the x value is equal to the function evaluated at the endpoint. If a function f is not continuous at a point c, we say that f is discontinuous at c is a point of discontinuity of f. So the point of discontinuity is the point where you have to lift your pencil to continue that graph. It's very important to also point out what the difference between an interior and an exterior point is. So if I have the domain range, say, from 0 to 4, the interior points are all the points between 0 and 4. So this would be the interior. It is important to point out, for example, that the point 0.000001 is an interior point of this domain, all the way to 3.9999999, and forever. Those are all interior points. An endpoint for this would be 0 and 4. These two would be the endpoints.